can just go up here to the top, and you can go to design and quick layout. And that's my quick layout. It's my favorite one. You know, it's the chart title, pushing all this stuff. I think I'll show this again real quick. Got all these options, got so many cool things. It's so nice.
Gary! I was just looking for the sports channel, Gary.
Hey everybody, so it's really bright where I'm at right now, but I got the green screen working really well. You can see, don't look at the chair, don't look at the chair, whatever you do. But so we have the green screen working again. I've got the speedrun stuff up. I know you guys don't usually see speedruns, but if you notice, I added one of the boss things that you can add. So if anyone wants to try subscribing to the channel, you don't have to subscribe. Oh, it's loud? Loud and clear, wait, okay. Good to see you. Good to see everybody. You know, I've got like a whole studio set up now. But so it's looking a little bit better now, and it took me like hours to figure out how to do a green screen properly in a tiny, tiny room. But can everyone hear and see me? It looks like everyone can. Since I'm doing the new setup, I'm always worried when I start streaming. Don't listen. And if someone wants, try to subscribe to the channel. You don't have to subscribe, but I'm wondering if the thing works, if the boss thing works, that when people subscribe, on which variable. Great step. Well, thank you very much, Quinlan. So it's a multi-purpose room right now. So one of these days I'll have an actual whole setup. I don't know. It looks like maybe no one's subscribed. I don't know, but I was wondering if that worked, and I really had no way to test out myself. People are saying, I'm not sure about letter D in writing the vanilla regression. I'm not, which variable to write before the, so it'd be the Y variable. Are you doing, it's a logistic on that one, right? Well, thank you so much, David. Oh, look at that. It did it. It did it. Did you guys see the points come off of there? Oh, it totally did it. So you have to like have subscribed now. I don't like and resubscribe. Since you're doing, if I remember that model correctly, Kyle, that one is it purchase? Is that what you're doing? Is you're predicting probability of purchase? So you're doing a, here's some big things people should understand if I remember the problem you're working on. You're predicting if somebody will purchase, yes or no. So you're going to be using ROC to judge these models. And then on top of that, so the purchase is going to be the Y variable. It's going to be purchase tilde dot. Does that sound right, Kyle? I think I've got the assignment over here I can look at on this computer. I've got about 10 computers around me right now. So only 3 computers. But if I know which one you're working on, and this is the right thing right here, you said part D. Yeah, it's purchase. Yep, it's purchase. Does that make sense? Yeah, so since it's a logistic model, you will, you know the data is trained. Definitely, anytime you're doing a predictive model, the data is trained. Anytime you're doing a predictive model, the data is trained. So awesome, and thank you there. I wish I could add points, but thank you for the sub right there. Yes, Ali, thank you so much. You can unsubscribe if you want. Anyway, you don't have to subscribe. There's no extra benefit. We're gonna hop over right here. So let me, there's the boosted trees, but we're gonna go back to it right now. So I should be able to go back to full screen mode. Is that button working? Let's find out. Oh, the button didn't work. I have to reset my buttons. I've been like reconfiguring everything, getting everything going, but I can still get over. Here, we'll hop back over to the slides. Okay, we're back here on the slides right now. Sorry, I'm gonna move myself a little bit this way. You can see my hair doing a little bit of craziness, but and the lights are bright, but the green screen looks to be doing pretty well, and you guys can maybe hear and see me better a little bit right now. And maybe I'll make a BAS 474 thing, but so do you guys like this a little bit better? Is this a little bit easier to hear and see me? Does it look a little bit more professional? That transition was awesome. It's cool. I made that in After Effects, so, and one of these days when I have a bigger room, I'll make it look better. Oh, thank you, David. So we're getting it. You're getting fancy. It looks great. Awesome. We're gonna keep it looking great. We're gonna keep adding new things. This is, I think it was Kyle. You asked me this weekend if I had free time, and I was like, I am reorganizing everything. I am redoing it all. So there we go. Okay, good stuff. Here, I think I'm gonna break down and shave. I don't know. It's been like a week, so I'm gonna shave one of these days. So we will continue on right here. Let's start talking about some boosted trees. This is where we ended last time. I've got the chat screen over here, so when you see me looking that way, that is what I'm looking at. Don't do it, Brian. Don't shave. It's looking crazy right now. Okay, here we are back on track, learning some new material. Fear to the You guys are awesome in the chat. Okay. So we have bagged trees. To review the last concepts, we have bagged trees and random forest. What is bagging? Bagging is, and I want to see it in the chat, for 100,000 points. We've been going crazy on the points. I want to see it. Remember, you get the points for chatting. That's how Streamlabs works, is it watches how many times you chat, and the more you chat, the more points you get. So I want to see it in the chat. What is bagging? What is bagging? Bagging is another name for something else. Yields an estimate of the generalization without really careful repeated. Yeah, you can use it. Yep, it'll do that because it does, like, it keeps a certain amount out. That is very true, Aaron, right there. And what it's doing is it's doing, for some reason the word is escaping me. I know how to do it. Bootstrap. I literally saw it on the slide right there. I looked over and I saw it. Like, I was like, the word's escaping me. It's another word for bootstrapping. So when we think about these bootstrap samples right here, the bootstrapping is resampling the data we already have. So we're resampling our current data to create new data sets, and then we're going to create these trees on different data sets. This is a huge thing. Bootstrap aggregation right there. Christian and Kyle, great answers right there. 100,000 both you right there. So resampling with replacement, Evan, 100,000. That's exactly what bootstrapping, i.e. bagging, is. We need to know these words synonymously right here, that when we see bagging, when we see bootstrapping, we know exactly what they are. They're just synonymous words. Bagging, bootstrapping, even if the words jump out of our heads, we should know sampling with replacement. Exactly, Dave, and 100,000 points. So what is a random forest? Well, random forest is going to go above and beyond with this. We're just doing kind of a review of last time. We're going to have the number of predictors to try here with mtry, and then we're also going to have the number of trees the forest is going to use. So all of these are going to be tuning parameters. It says parameters on there, but I want you to know of these as tuning parameters. We're going to do the activity today and focus in on this, and we don't have class next time. I know, crazy. It's like we only have like 4 more classes left. But with this right here, you're looking at the different things to try. And the way I describe this, and maybe this is an example I haven't done as of late. Go Cardinals. Yeah, you can see right there. I got this shirt for like $5. I still like it though. 100,000 bucks right there. So let's go in here. We've got the lab pulled up. Move this for a second. The way I like to describe tuning parameters is to talk about them. One of my keyboard things was not up. The way when we talk about tuning parameters is I talk about like making a cake. When you make a cake, I want you guys to think about some possible characteristics for this cake. Like, I want you to tell me flavors for the cake. Who can give me different flavors of the cake that we could make? So let's go here and make expand grid. This is how you make a tuning grid right here. And we're going to go to flavors. And what are some flavors we could make? Any flavors? Chocolate. Chocolate. What other flavors could we make? Red velvet. It's good flavors right there. And it should do it. We'll do an underscore. We'll be good there. 100,000 points, all these answers. Tuning Oreo. Okay, now I need an icing flavor. Or let's choose icing. Like, I need some icings from everyone. So I need some icing. We'll go with vanilla icing. So if I know how to spell it, other people are spelling it right. Vanilla cream cheese. So now we got cream cheese. And what else we got? See, everyone's talking on this right here. Okay, now I need... we're either going to overbake or underbake this cake. We're not going to go in the middle. So I'm sorry for those who want the cake baked correctly, but we're not going to bake it correctly. We're going to give it a certain bake, and the bake is going to be... Dave wants over... gets the cake. What is it? Cake is a lie. Is that right? Wait, what? I think the pie is a lie. I'm sorry, my mind just underbake. We're getting votes for underbake, right? I'll go underbake. I'll risk that salmonella for, I don't want that overbaked cake. Okay, so I want someone to tell me, for 1,000,000 points, how many combinations of cakes are there? How many combinations of cakes are there? Oh, is there? Yeah, there is. David, you're right. Sorry, my brain wasn't working. My brain, I had a wrong answer in my head. I did the math again. I looked at the numbers wrong. I thought it was 322, which changed it. Yeah, sure, everyone's getting 1,000,000 points. Everyone's right. Yeah, you're right. There it is. And I've got an error on my bake. Where's the error symbol? Oh, here it is. Okay, so now let's do it. There it is. Didn't have a symbol, so we weren't separating the variables. Don't answer until you guys are awesome, but I want you to look at what this expand grid does. And you're really getting it if you know what's going on right here for those who've been doing the assignment and seeing the output. In one of the outputs, you have 6 different knobs on the one tuning parameter, like 6 different values. And then the one you have 11, so that makes 66 different models, 6 times 11. You would think it'd be like 6 times 10, but 6 times 11. But it's just the different values you can put on the tuning parameter. So what do we have right here? It's all the combinations of cakes we could make. So when you look at this right here, it's every single combination of cake, and that's it. That's all, every combination of cake we could make. So at least from these tuning parameters. If you notice, why are they called tuning parameters? These are the different things we can adjust when making our cake. And it kind of helps to write it like this sometimes because it's easier to read. Like your first parameter you're going to tune, put in the levels of it, comma. Your next parameter you're going to tune, put the levels of it, comma. And I like to enter, makes it really easy to read with the format. And formatting just super helps things. So that is what tuning parameters are. And we go back to the slides right here. And that's what we're talking about right here. These are the different knobs you can dial up and down on the cake being the model. And the number of trees you're going to try are going to be your points reduce for using, don't use profanity. I don't think it does that. It just, I can block stuff, but we might, if someone came in here and started dealing with, yeah, mods will do stuff. But number of trees, not entry. Now when we get to XGBoost, it's going to be weird because it's going to want entry plural. And then mtry is just going to choose how many of the variables it's going to select per tree. And we can tune this and just have fun with it. You'll see all the code right here. We'll be doing some models a little bit later. So we'll get to see some more code on this. And I'll make it bigger so you can see it. We've got right here the importance. Just kind of tells us, I usually like to look at importance to tell me what variables I should take a look at. It looks like when, just imagine telling someone about this. You'd say the most important things to look for in your personal identification of junk emails are emails that have things like exclamations in them, $signs, free, remove, a long rung of capital letters, things like that are the most important, with the most important being exclamations and $signs. So those are really good kind of important variables in deciding if something is junk or not junk. So just think about this right here. The top things could be used for later analysis. We could maybe try to figure out why. We could do, explain it. We could do descriptive models and make explanations as to why these things are happening, or maybe take samples and try to look at them. So I usually think of this as like a post thing. We don't do a ton of analysis with this, but it lets us understand kind of looking at the model. It's more of a descriptive nature of the model than it is a predictive, because it's not making predictions, it's just telling you, describing what is most important. So although we're in predictive modeling, we still do a little descriptive, like why does it matter? So we see all this right here, the costs and the benefits. You can see, I have noted it's gone. So pros and cons, the models are very flexible, often take benchmarks if you need a decent model. The biggest thing I'd like to say about these is this is really the power of statistics. This is the power of predictive analytics. This is the power of what your computer can do. Now, anyone who watched, I think Connor was there yesterday, and Joel, I think, was there in the online office hours yesterday, and I did a support vector machine model, which we'll be doing next lecture, and it took, I promise you, about 5 to 6 minutes. So with that in mind, these models can take a very, very long time to run, and the same thing goes for things like XGBoost, which we're right about to look at. Once again, you don't get a good visualization of the model here, and then we do have, this is a huge thing for any 201er, maybe Julio's here right now watching this, who knows, he jumps in the chat and says, hey. We don't put what types of variables in decision trees. Go back to 201 for 1,000,000 points. Yep, it's on there. Yep, it is, Ali. And I did a lot of the assignment in yesterday's office hours. So I talked over a lot of it, showed some of the code, went through it, explained a lot. So if you look at yesterday's office hours, I did a lot of it. Great job, great question, Ali. What variables do we not put in decision trees? What variables do we not put in decision trees? You don't want to put these in for 1,000,000 points. Who knows? Who knows? Starts with an I. It's a variable type we rarely ever talk about. Identifiers. Connor's right. We don't put identifiers in decision trees. So we don't put identifiers in decision trees because they have so many levels to them. And that's what you see right here. The model will be biased towards those. The reason being is that when you look at the way trees work, I've got to go way back here in time to look at how trees work. Trees work by splitting stuff, which remember, a forest is just a whole bunch of trees. Trees work on splitting stuff based on how many whats there are. Trees work on splitting stuff based on how many blanks there are. Something with levels. And you'll see it in here, why, we mentioned this last class, why GPA, I know that's hard to read, and the unique levels, you're right, how many unique levels there are. So since this has more unique levels, I know it's quantitative still, but there's more unique quantitative values to high school GPA than there are unique values to the college or ACT right there. Don't worry, I can't even read that, but that says ACT down there. So since it says ACT down there, we can see, there we go, we can finally see it. I'm blocking a little bit here now, but since that says ACT, there's less unique values, and so all it's doing is splitting between these values, and there's more ways for it to split on high school GPA, so it's more likely to split there. The same thing goes with categorical variables, and how many levels are there? Like if I have 1,000 data values, 1,000 rows of data, and I have identifiers, how many unique values are there? How many unique values are there if I have 1,000 rows in identifier? How many identifiers will there be for 1,000 rows? How many unique levels of identifier will there be for 1,000 rows? Any ideas in the chat for a million points? Oh, Connor's got it, 1,000. There'll be 1,000 because there's just as many. Everyone gets a million right there. So Yulia and Ali and John. So there's 1,000 levels. So when you look at this right here, when we're saying that it's going to be biased towards categoricals with a lot of levels, the one that will have the most levels is an identifier, because an identifier is unique for everything. So it's not, you just don't want to feed it identifiers. There can be stuff with a time series to identifiers. There can be kind of like identifiers that have, like, if you give people a number as they walk into a room and you want to see how people do on a test, then that's also an identifier, but it also has like, it also serves as like order of individuals, which maybe there's some time order element to that. So at that point, maybe that might be a good variable, but identifiers are rather problematic because they'll kind of take over the tree. We can just see how the trees are generally doing right here. As you increase the number of trees in the forest, and these are different types of models right here. We've got bagging, we've got random forest, we've got bagging, we've got random forest, and this is the OOB different data sets right here. So you can see it generally does better and better as we have more and more trees, but you get this diminishing return. You get this like leveling off. So how many trees do you need? Well, it's like getting larger and larger sample sizes in statistics. It's like, well, if you go from 10 to 100, that's great. If you go to 100 to 1,000, that's good. And you go from 1,000 to 10,000, it's like, well, you're getting diminishing return, and your computer's just going to get angry at you. I mean, you know, it's a computer, so don't worry. But still. Regardless of the model, the out-of-the-bag estimate is generally over-optimistic. And this is what was mentioned earlier. The out-of-the-bag estimate is your validation, because we section off some of these with the bagging approach for the training and some for the validation. This is the out-of-the-bag portion. So we have where we have our training data and we have our validation, and the validation is going to tell us an estimate. And since it's overly optimistic, we might overfit our model. We might say like, okay, this model is going to do this well, and it only does this well. So the biggest thing, we need to know what overfitting is really well. Overfitting is when you get an ROC of like 0.90. And what does that mean? We talked about this a lot yesterday. Million points in the chat for whoever can interpret my ROC of 0.90. Who knows what it means to have an ROC of 0.90? The model correctly, or the percent of time, who knows what an ROC of 90% would mean? Oh, it's silence in the chat. This is a 5 million point question, because it's basically a homework question answer. Well, what does it mean specifically? Like, it's something about the way it does the predictions and the probabilities. Ooh. Oh, I see. This is a knowledge gap. So I'm going to go over it briefly here. So it sounds like this sounds a lot like accuracy right here. When you talk about AUC ROC, and we drew this out yesterday, so I might not do it too much here. Well, let me do I did a really good example yesterday, I feel, and I'm going to do it again here real quick. So closer, David. David's pretty close. Everyone's getting a million point, took a shot at it. So, and then someone said to me yesterday, why would you ever use accuracy? Well, it's easier to understand accuracy. So I want us to look at the following model right here. So this is the predictions from the model, and we're predicting the yes class. So we're predicting the yes class, and I want us to look at this right here. So does it correctly... Well, since it's AUC, it's always going to be categorical. Since it's, well, what it's going to do, here, John, we'll get real specific on it, is if you look at this, does anyone know what the AUC of this model is? And I have to give you some probabilities right here. Well, actually, I don't even have to give you probabilities that they can order. Um, it's close. Here, I'll explain. Ready? So I want everyone to think about what the AUC of this model is, and I hope this example helps out. Close. Okay, I think I know the AUC. So these are the probabilities, and we're predicting the yes class. Ooh, let's do this. Oh, this is going to be interesting. I'm going to make this very interesting. This is a very interesting model right here. Okay. So people are saying 75%, but I don't think it's 75%. I'll explain why. Everyone's saying 75% in the chat. I don't think it's 75%. So I'll double check. You guys can be like, Brian, you're wrong. And I'll be like, oh no, I did the math wrong. But I think it's another answer. Who knows for 2 million points? We're going to have to go into detail here. Oh wait, Nicholas, I'm going to give you 1 million points for that. And Joel gets 2 million points for that right there. Joel is right on the AUC of this model. So I want us to look at all the pairwise comparisons. Ali gets a 2 right after there. We're cutting off the 2 million now though. So we go right here and we look at this yes, and we look at how often it gets the right amount. We look at its pairwise comparisons right here. How often is that yes properly ranked? How often is that yes given a higher probability than the no classes? That yes is given a higher probability than the no classes 2/3 of the time. And now that's actually true for all the yeses. If you were to take another random yes right here and say, how often does this get a higher probability than the no classes? So you see I have them ordered, and then this yes right here gets a higher probability of the no classes 2/3 of the time. Same thing goes for the one right below it, and so that's why I did this order to it. So when you draw your graphic right here, I want us to think about this. When we draw out this, there'll be 3 spots here, 1, 2, 3, 1, 2, 3. And these are they can be like your false positives if you go through them. They can be the true negatives also. It's just a few ways of labeling it. And then true positives over here. So, but if you go through it, then you've kind of gone through a false positive. So it's either you can write false positive. I think most of them I've been looking at lately show true negative. And I did write one with false positive, so I hope I didn't cause confusion. But tell me, I want us to start going down this way. I want us to follow this arrow right here. As we follow this arrow, what is the first thing you hit? A true negative or a true positive? What is the first thing you hit right here? A true negative or a true positive? A true negative or a true positive? I'm going to clean up my graphic here because I want it to look very accurate. And people might be saying in the class, you're going to hit a true negative. So when you go from here to here, you'll hit a true negative. And then you go straight through what? You go straight through 3 whats? You go straight through 3 whats? Let's see you guys say in the chat. You go straight through 3 true positives. And then you hit 2 whats? You hit 2, just follow the arrow downward. You hit 2 true negatives. That's so weird. And then I wonder if I do this, if I do the red pen again, maybe I do a box right here, and I do a shading underneath it. It'll make it appear. Let's see. It did. That's super cool. Okay, so I want everyone to tell me if that's a 1x1 grid right here, what percent is that rectangle in that 1x1 grid? So remember, these are like, they're all like 0, 1, 2, 3. That's why I redid it a little bit. I want everyone to tell me what percent is shaded underneath that curve. And you're right, it's 66%. And so you can see right here that we were actually able to calculate it this way, and we were able to show that the yes class gets a higher probability than the no class 2/3 of the time. Now, sometimes I'll say it like we properly order the probabilities, or the probabilities are properly ordered 2/3 of the time. But you have to mention the probabilities that the yes class receives a higher probability than the no class 2/3 of the time. Can you do example of false negatives or false positive? Well, right here, great question, Joel. 1 million points right there. This right here is a false negative. So this is a false negative, and this is a false positive. So right here, and if you just think through it, you'd have to, that's why sometimes I talk about it. I think it's better to put true negative. As I was looking through my examples, I was like, how can I teach this better? How can I communicate it better? Usually we think of true negatives or false positives, false negatives, as in when they get the wrong probability. Well, A true negative, if we think it's positive, will be a false positive. So does that make sense, David? And I hope I haven't added to confusion. That's why I think when I was like, oh, I could just do the same thing I did last time, but it's going to be better if I put true negative down there, because these right here especially, we don't treat these. These are true negatives, and we don't identify them as false positives. So something can be a true negative and predicted to be negative. So let me repeat this. If something is a true negative and predicted to be negative, then it's accurately predicted. If something is a true negative and predicted to be positive, it's a false positive. So a true negative can be a false positive if it's predicted to be positive. A true negative won't always be a false positive, because sometimes, like these down here, these are not false positives, they're only true negatives. This one right here is a true negative up top, but it's also a false positive. The split always happens at, yep, exactly. Great answer right there, Joelle. I did it a little bit differently today than yesterday if you watched the video, because yesterday I didn't, this one has a different accuracy. We'll calculate that here in a second. But the split would happen right, we'll put a black line right here. So this is where I did the 50-50 split. What would the naive predict in a 50-50 split? That's really great question, John, right there. The train actually uses like a coin flip. And so we do say in the notes certain things, but then Dr. Petrie analyzed it further, and train uses a coin flip, and we actually had problems. That's not 50-50. Oh, no, but that is where the probability of 50% would be. So this is where somewhere in this area would be where the 50% probability would be. Does that make sense right there? So these are the probabilities assigned to them. It's a weird looking model. So the 50-50 is somewhere in this area. So it's somewhere in this area is where 50% would be. So it's not 50% of the data is above and below this. These are the predictions for a very small model. Why is it better to use this compared to the naive? It just depends. This one right here, oh wow, the naive might just predict yes, but this model right here, is it better than the naive? Well, it actually does look better than naive, because if we draw what the naive would do, the naive, we put a little line right here through this, and the naive only gets about 50%. The naive would give, actually the naive wouldn't, I don't even think you can compute it, because the naive would get everything a 50% probability, so the naive doesn't really even order the AUCs. And does that make more sense? Have we brought clarity to this a little bit? And does everyone understand why 50% is there? Because we're doing it between 80 and 48. So does that make more sense? And so that would be the AUC right there. That's kind of most likely by random chance. And another big thing about this is we should be able to get the accuracy. Makes sense to me. Good stuff. Good stuff. These are complex topics. That's why we review them so much. So I never want to just tell you guys something once. I want to go over it again and again. So now if you'll notice, I want to know the accuracy of this model. Which model performs? Yep, Joel, we'll look at that here. It's a great question, because I think we're going to do that here in the activity. So we'll be doing a lot of that. So, and keep emailing me. A lot of people, Con and I were emailing a lot this morning. I think other people have emailed me. Keep emailing me questions. What would be the accuracy of this model? And I think, yeah, what is the accuracy of this model? Who knows the accuracy of this model? I'm going to erase, and we're going to talk here about the accuracy of this model real quickly. What is the accuracy of this model? And then I'll kind of answer Joel's question too as we do that. The accuracy of this model, we have to see the predictions of it. And here is the accuracy. The accuracy is what for a million points? Who knows? 50%, John, you got it right. The accuracy is 50% because it is right 50% of the time. The model is accurate. David, also a million points. There we go, Connor right there. So a million points. The accuracy is 50%. The model accurately predicts the yes class, no class 50% of the time. Yulia, a million points. And so now we get to Joel's question. How do we know when a model performs better than others? This is a big thing right here. We need to kind of look at our summary statistics for the model. The big ones we have are going to be the RMSE. We'll go back to black right here. RMSE, but I don't think we're using that this assignment because we're doing categorical models, logistic models. So we're going to use either accuracy or we're going to use AUC. Now, whenever we have these measures, all of these measures come with a measure of what? Uncertainty. So we want to look at all of these measures' uncertainties, which will be their standard deviations. So your standard deviation of your RMSE is your uncertainty in your RMSE. Your standard deviation of your accuracy is your uncertainty in your accuracy. Your standard deviation of your AUC is your uncertainty in your AUC. Because it's like saying to someone, that steak dinner will cost $20, but I could be off by about $5. you're saying amount of uncertainty. When you say the AUC is 0.80, but you have a standard deviation of 0.02, you're saying, well, I think the AUC is about 0.80, but I could be off by about 0.02. So you're just saying about, I could be off by about this much. So then what we do is we take, and let's go here. Whenever we want to compare models, we're going to go and take our best model right here usually. So we've got model 1, which can be our best model. And we're simply going to take whatever measurement we have from this model and subtract it from model 2. So, and that's just going to tell us the difference. And then we're going to standardize these differences. Joel right there, 1,000,000 points. We're going to take model 1 minus model 2, take their difference. And this is the difference between their AUC, their RMSE, their accuracy. We're just looking at the difference between them. Just look at their difference. Boom, right there. And then we should mention also that we want to take the larger standard deviation of model 1 / model 2. So whatever the larger standard deviation right there, Connor, 1,000,000 points. Great job helping each other out. So all we're going to do is make a z-score from this. All this does is give us a z-score. It's just a standardized unit of measurement to tell us how many standard deviations they are away. And then we will think that they're basically similar if they're within what of each other, plus or minus this. They're basically identical, not much of a difference if they're within plus or minus this. And remember, you get all of this in the output. One standard deviation right there, 1,000,000 points, all those answers. We would prefer a higher AUC because remember, AUC is the model accurate, or the model accurately gives the yes class a higher probability this % of the time. And the yes class should receive a higher probability. Saeed and Aaron and Caleb and Christian, 1,000,000 points. Keep those answers coming. Remember, you get the Streamlab points too, which I will look at for how much you guys are talking in the chat, and I really appreciate it. And you can check those points like during class, after class. But you want a higher AUC, you want a higher accuracy. The only one you want lower of is RMSE. You do want to lower RMSE because that is root mean squared error, and you want lower errors. So all this good stuff right here. Boosted trees is where we ended last class. Spencer, 1,000,000 points right there. And boosted trees are going to actually have trees learning from trees. This is insanity. Trees learning from trees is... It still just boggles my mind that we came up with these algorithms. Like the amount of work that goes on in the background when this happens is insanity. So we got each tree is kept very simple. When you look at it, as I'll show you, here's trees. We can control the interaction depth. The interaction depth of 1 actually has no interactions. I know it says interaction depth of 1, but it's just doing 1 split at the top, which doesn't have any interactions within it. And then you've got an interaction depth of 2. So all of these are the trees that are creating the model and making predictions. So we go back up to here. Each tree is kept very simple. The entirety of the training set, as opposed to bootstrapping, is used to build the model. Predictions are not the average of many trees. That's bagging. Rather, the model predictions are based on a weighted sum. You'll see that here in a moment with an example. One way to think about this, and this is all you really need to know about this, so what you're going to do is you're going to do a garden each year. So this is the way I like to think about this example with boosted trees. Did anyone ever have like a home garden? And like you try to plant something, it just doesn't grow in the garden, or you get the wrong fertilizer, or you just like you didn't water it enough one season, and you're like, man, that garden last year just didn't do well. So that garden just didn't do well. And no one had experiences with that. Am I the only one? I'll tell you guys a really quick story. My dad's gonna hate this, but we can relate. Yeah, John, you told me about that. So yeah, you know it's all about, John. So we used to have a home garden. I think it's why I love hot peppers. I don't know when I first started loving them, hot food, but my first memory of liking hot food was we grew jalapenos in the backyard, and man, were they hot. I don't know if I've had I've never had a Carolina Reaper, but I've had habanero and stuff. I still think habanero's hot. Ghost pepper's really hot. Carolina Reaper, I'm sure, is insane. I'm a little scared to try it these days, maybe. I don't know. I need to try it. I like hot food, right? So, I mean, but there's hot, and then there's not fun hot. But, so my dad said one day, he said there was a big weed growing up in the backyard. It's been growing for quite a while. I finally went over it with the lawnmower, and it was a blueberry bush that we had been growing for like a year and a half maybe. And it was just like getting bigger. I mean, it went from like here to here to here. And my dad finally just went over with the lawnmower. And I was like, no! Anyways, Dad, why? But, so here's the point of all this. We had to start over. That's the point of the story. So You can relate to that. So you have to start over. So what do you do when you start over? You take all your knowledge. You take all your knowledge from that blueberry tree that your mom or your dad destroyed, and you take all of that knowledge and you make a new what from it? You make a new tree. And then guess what you do after that new tree? You run it over with the lawnmower again. And you know what you do? You make a new tree. You know what you do when you learn from that tree? You run it over with the lawnmower again and you make a new tree. Each tree learns from each previous tree. So each tree is going to learn and learn and learn and learn. But we've got some key important stuff right here. That's on the next slide right here. The learning rate. John, do you want to spend your whole life building that garden? Maybe John does. Maybe John wants to spend the next 90 years building a garden and learning how to build that garden. But then someone says, I don't got time for this. They say, I don't got time. They say, I only got 5 years to learn how to garden. So they're going to have to learn really quickly how to learn how to garden. And this is what we call the learning rate, which is a tuning parameter, just like we had over there, the interaction depth is a tuning parameter. So someone could say, I want to learn really quickly and learn it in 5 years. And someone could say, I want to learn it over the course of 100 years. Now, this will control how many trees it takes. Slower learning rates require a lot more trees. Faster learning rates don't require as many trees. So usually we get a smaller learning rate having a better model. Like if you think about who's going to be a better gardener, the person who learns over 100 years, a very slow, small learning rate, or the person who learns over 5 years, a very quick learning rate. We would think that smaller learning rates. Now, if you have very large data frames, all of a sudden now it can be problems. So hopefully it wasn't destroying the bush, so the blueberries. No. So you missed the story, David. My dad destroyed our blueberry bush, and then John's mom destroyed them also. It's no luck with those. So long time is better. Yeah, and the reason people might say, well, if it's better, why don't you just always use it? If it's better, just keep using that. Million points, Joel. Great comment. The reason is it's computer intensive. It's going to take a lot of time. Especially you get into this, we talk about big data, and you go to big data, well, you might not have the ability to do a very long learning method. It might just take too much time. It might be too hard on your computer. So yeah, it depends. Always look at your data, always figure out what's going on, everything right there. Cost more time, definitely. More time. Great comment right there, David, million points. So we got here the interaction depth, and this is what we were talking about previously. So let's take a quick look at it. We've got here an interaction depth of 1, interaction depth of 2, interaction depth of 3. I rarely see things get much larger than this. I mean, you could do a expand grid on all this right here, and David right there, million points. You could do an expand grid and do a whole bunch of different values. And this is the biggest thing. You'll see lambda is the tuning parameter. We'll show this in an example right here. But you're just going to keep building the trees and learning. I think the next slide, here's the example, is just showing you what's going on right here. You literally take the knowledge from your tree, and you're going to go here, and we know the actual value right here, and then we're going to get the tree's prediction right here. And then if you notice, this is the lambda tuning parameter, which is used throughout. And it's kind of, if you look at the value right here, as we go through tree after tree after tree, the value of our prediction is kind of getting closer and closer to the actual. And that's what we want as we tune the tree, that it's going to use more and more trees to make this choice and put everything through tree after tree after tree after tree after tree. And each tree slowly learns from the last tree, because if you look, the prediction this tree is making, our new value of predicted y, which is the new predicted y value right here, is using the old predicted, which was the previous new predicted. It's a little hard to follow the notation if you kind of, I don't know, as I was like researching the slides, I was like, wait, the new predicted is now the old predicted, because every tree learns from every tree. And that's the concept you need to know. You'll never solve the math on these. I would hate a test question like this. There will be math on the test, but we let the computer do it for us. We know that the predictions from the previous tree are going to be used with the value of lambda right here, which is the learning rate. And if you think about this, if you turn the learning rate way up, well, then it's going to just take most of the prediction from the first tree and just use that immediately. And so you're going to get the prediction of your y value very quickly from very few trees, because how much of that prediction is it taking from each tree? Small learning rate means a small amount of each prediction. So as you go through trees, the predicted value of y would change less and less and less. I mean, it'll change at a similar rate, but it's going to have very small incremental changes, where if you have a high learning rate, which is going to be your lambda value right here, tuning parameter, then it's going to get big jumps because each tree is going to massively change the predictions. So all of these are tuning parameters. These are all tuning parameters, the interaction depth and the learning rate. The learning rate is typically a small value between 0.01 to 0.001. Slow learning means it's going to take longer, more trees. A very large number of trees may be required. However, too many trees will make the resulting model overfit, so we got to watch out. So guess what? We've got right here, do we show the tuning parameters again? Where's those? There we go. This is GBM, so we're still in, boosted trees. So gradient boosted models, that's right here. What's GBM stands for gradient boosting. So we've got here the number of trees, the shrinkage is the learning rate, and then we have here the interaction depth, which is just the interactions you were seeing earlier. And then what does the last one stand for? The minimum number of observation in node. I always had a hard time reading that when I was first doing this, number of min observations in node, because it's hard to tell where the words end, but it's how many minimum things we would have in one of these right here. So all it's talking about is the amount of observations, which we can see down here. Oh, here's a good logical question. Could the tree on the right be produced if min observations has a tuning parameter of 15? Could the tree on right behind me right now be produced if number of min observations in node was tuned to 15? Could this tree be produced right here? Could it be part of the boosted trees? Yes or no? Million points first person. Could this tree be produced? We could show you tuning parameters, and the answer is no. So these are the kind of test questions I like, is I could give you a whole bunch of tuning parameters. I could say the learning rate is this, the blah, blah, blah is this, the blah, blah, blah is this, could this, and all those right there. Jessica, Aaron, and Joel, million points, and Elliot, and John, and Allie. So this is a really great test question in my opinion, because all you have to do is look at this, and you have to say like, okay, it can't be produced because this tree has a minimum observations in the node of 11, or that's, I guess that's its minimum, and that could not be produced because we set it to 15. So this would not be what the model would do. It would do something different than this. So knowing what these tuning parameters do is key. We need to know exactly what's going on. I'll go back and look at the notes here in a second, see if there's anything we missed. But the biggest thing I tell students to focus in on with this test is know what each model does, like a description of it. Take these notes down. I want to see in the chat for 1,000,000 points. You got to write both these things, write in one thing. Know what each model does. Like, what does a boosted tree do? What does a gradient boosting do? And then know the tuning parameters for each model. So I would have notes on this right here. I would have these memorized. I mean, I do have them memorized, but I would know what they each do and what's the point of them, because that's a huge thing for all these models, because that's like knowing how to work your stove. It's like, okay, here's the temperature, here's the time knob on the stove, here's the humidity on the stove. It's like knowing what to tune your stove to. So you need to know how your stove works, notes on the slides, potentially, You got to put the full thing. You got to say, know what each model does and know the tuning parameters for each model. So we should have a good understanding of what each model does. Yes, please put these timestamps. Thank you so much for everyone putting timestamps. A lot of people have been doing that in different classes and everything. I really appreciate it. There's the tuning parameters. And this is on the full notes. This is slide 118, 119. So make sure to put it in afterwards. You can watch the video and see where people mark timestamp, but then make sure to come back afterwards. So with just 4 tuning parameters, Evan right there, 1,000,000 points. We've got 4 tuning parameters only, and we have 192 models to look at. That's insanity. You can get way too many models way too quickly, and this is where we get into problems, is that we're going to see a lot of models being used right here. And what do we notice? We can get a view of how exclamation point, I love this about it actually. It's actually kind of showing you where we would get the predictive of exclamation point really dropping off. So if you look right about right there, I'm trying to put a line on it. We might need to zoom in on it. I was trying to do it near 50%. I can probably do it better now zoomed in. But it looks like even after 1 exclamation point, that's like even before 1 exclamation point. So if there's a single exclamation point in your email, then it basically predicts it as junk. So basically, don't open emails with exclamation points. It might be in like the title of the email. I don't know exactly how this model is kind of scraping that, but you can see right here, we can get some output from the GBM to tell us what's going on with the relationships of each variables. Now, this is going more into a descriptive model right here, telling us like what is the relationship exclamation points have with the probability of something being safe. Reason it's safe, you might be wondering, wait, Brian, you kept saying junk. Because this model, million-point question, why are we predicting safe? Oof, this is a good question. Why are we predicting the probability of an email being safe? It works the same with no and yes. The same reason we are predicting yes. Why is it that we are predicting safe for this email, million points? Why are we predicting the probability of safe and not the probability of junk? Safe comes after junk alphabetically. Exactly. Million points, John, right there. You are correct. There we go. Last alphabetical, Will got it too because logistic, yes. David also. Level of interest is last in logistic. David and Julia, all million points. Yes. That's how I know we're predicting safe. I wish it said over there probability of safe, but you have to know little things like this, like, wait, why are we predicting safe instead of junk? So, and it could be not junk also, because that would have N at the start of it, but logistic level of interest comes last. You guys know my stuff. That's how we remember it. Logistic level of interest comes last. And the level of interest is what we're predicting. So you can see right here, we've got right here, GBM, we're using the GBM. We can see also we do it with train and other slides. So you've got y tilde x comma data equals. Distribution is Bernoulli trials. And trees right here, interaction depth equals 5 and shrinkage equals this right here. This is just one model not being tuned across it. And all this stuff right here, if we were to tune it, could take a very long time. And then we've got XGBoost. Now we don't go into this too much because there's so much to XGBoost. Like XGBoost, we could probably spend a week on XGBoost. So XGBoost is used in more than half of the winning solutions on Kaggle as of March 2016. Do you guys think this is a pretty good thing right here? And we looked at this last time. We're going to hop to activity here in a moment. We've got enough time, I think, to do. And I'll probably be doing a stream where I do the full activity. So we'll start doing it, and I'll go through most of the solutions. And then I will post a full stream of me doing all the solutions. Yeah, it's really awesome. All it's doing is it's going to do regularized regression. What does regularized mean? We're controlling for what? When I say regularized regression, you should know instantaneously we're controlling for this with regularized regression. You must know anytime someone says regularized, million points in the chat, first person only, we're controlling for the this trade-off. You should clue in when I say that. You should be like, oh yeah, that's what it is. When I say this trade-off, you should be like, oh, the blank trade-off. Which means we're gonna boom, Allie got it right there. Nice job, Allie. You got the full thing, you got it. So the bias-variance trade-off, or variance variance, but we should know all what it is. And if you have a model that takes too much information, it's going to be low bias. If your model takes no information, it's going to have high bias, but it'll be low variance. It's like you get more bias, you get more variance, you get less variance, you get less bias, you get more variance. They trade off between each other. So here's all the parameters right here. Last time I did it improperly because I think there's 9 we figured out. There are 9. I've done some of these, but man, I guess it's like one of my cousins is a professional chef, and it's like sometimes, you know, like we had one like family get together where we made pancakes. So we were making pancakes, and imagine if she were to pull out like her like $10,000 culinary knife set or something like that. So it's going like to the beyond. Like XGBoost is like so powerful sometimes and so labor intensive. And if you want to win a Kaggle competition, like if she's trying to win some sort of competition, she's going to do it either min-child weight is a oh god. That's like the splits, I believe. Basically the minimum number of individuals allowed to be in a partition. Yep. There we go. The minimum number is a split. That does sound weird. So I didn't choose the parameter names. But you can see all of these right here. But it's super powerful. Similar to CP, so you've got your gamma. And so right here, if you want to practice up and get really good with predictive modeling, this is probably your best thing. We should know lambda, we should know alpha. Those are just your lasso and ridge trade-offs right there, so we can put those through. XGBoost can be thought of as a more generalized implementation of tree models, as we've discussed. So all this good stuff right here, and I think that basically does it. The regularization is probably the biggest advantage of it, because the regularization is going to make sure we don't what our model. The regularization is going to make sure we don't what our model. This is key, million points. Regularization is going to help ensure that we do not Overfit. David got for $1 million right there. Overfit our model. There we go. I'm going first person lately. So that's the biggest thing we should know is that regularization. Remember, if you are chatting, you get the Streamlab points, which I will be counting, and it'll be weighted on everybody. And they'll be really fair across the board. So a lot of times we would think that this is best, but sometimes it just works to use a simple model. So see how you do on the XG parameter tuning process is, there we go, is very time intensive, keep saying. And here's some examples of tuned models. I want to hop to the activity though, because I want to start showing you guys how to do these tree-based models. I think XGBoost, let's look right here. XGBoost can be done, I think it can be done in train. Let me pull this up. Let me show you something crazy, John. If you want to see what can be done with train, oh my gosh. So wait, I'll show you guys what can be done with train. This is why I don't know everything. So there's a whole, here goes, this it? I think I found it. Yes, okay, cool. Okay, John, we should be able to find it right here. Let me bring it back up the chats. Okay, so XGBoost is in here, I believe. And if we go XGBoost, there's extreme gradient boosting, and it's under train. There's other packages that have it too, and we see the 9 different ones. Are these 9? There's 1, 2, 3. There's 9. So there and there. Did they change the name of it? Did they? They might have changed the name of it. So sometimes they'll update the names of these things. So min sum instance, all these things right here, extreme gradient boost in there, extreme gradient boosting. This is why I don't know everything that can be done inside a train, because these are all the different types of things you can build. These are all the different methods. So you've got hybrid neural fuzzy inference system. I have no idea what that is. I do know what fuzzy means. I do know what neural means. This is like the way in which we do cluster analysis, and fuzzy clustering allows for, it's really, Dr. Seaver does a lot with a fuzzifier with kind of, you've got this more of a boundary where things are less pronounced between the clusters. You're kind of making a fuzzy boundary between the clusters. So I know what a lot of the terminology means. Of course, I know what a neural net is. And then I guess they're putting the two together, but I've never, till this moment, heard of a hybrid neural fuzzy inference system. But that can be done with the train package, just like that. And then you've got tuning parameters, number of fuzzy terms and max iterations. So you can look at all these different types of things right here, and this is why I don't know them all, because there's so many different tuning parameters, there's so many different models. So what should you know? Here's the thing. You should know what a multi-layer perceptron network with weight decay. Now, what a perceptron network sounds like to me is going to be a neural net. And with a weight decay, it looks like they're doing some ensembling of it, and there's a decay between each model. So I think they're using ensembled perceptrons, and a perceptron is what created the neural net. We'll hear about that later on when we talk about the neural net and the perceptron that preceded it. So with some decent idea, I've got kind of an idea what this model does, but I don't really know it well. I've never done one of these models before. And then I should know what all these tuning parameter does. Well, it's definitely a neural net because it's got hidden layers. So we can see it right here. It's got a learning rate. We kind of know what learning rates are right now. And then I don't know what the row parameter is, learning rate decay, activation function. So once again, you need to know for every model that's in your toolbox what it does and then what the tuning parameters are. That is so key. And once again, there's so many models on this list that I know a lot of them, but whenever I see like regularized, if I type in here regularized, there's regularization on that. That's controlling for bias-variance tradeoff. And you can see how often regularized is on here. If you look at the top of my screen, it's on 32 different times. But deep boost, I have no idea, number of boosting iterations. So it looks like it's trees learning from trees, tree depth. So that is the what? Ooh, million points. What did we call this just a moment ago here? What is tree depth? Someone tell me what tree depth is for 1,000,000 points in the chat. Then we're going to go do the activity for a while. Someone tell me what tree depth is right here. Who knows? We called it something just a moment ago. Interaction depth, Aaron, you are right, for 1,000,000 points. That is the interaction depth. So we've got regularization on boosted trees, and we've got right here a loss parameter, which is going to be for the regularization on it, it looks like. Because actually, yep, there's the tree depth regularization. Whoa. I don't even know how tree depth regularization works. So that's that is a bias variance trade-off on the tree depth regularization. Wow. L1 wow, there's so many things right here. So, man, I look at this stuff and it's like some people just go to like, stores to look at stuff, and I look at all these different models, and this is like my model store when I look at it, and I'm like, all these different things we can do. So cool. Okay, let's hop in here and start doing the lab. We'll be able to do, I think, a good bit of it right now, but I need your guys' help with the lab. You ready? So we're going to do the lab right here, and I'll record the rest of it. So wherever we get to, I'll pick up right there, and we will have the rest recorded to complete and kind of watch and learn from. So I think that's a big, big help, and it utilizes class time really well, I think. So we've got a partition currently containing the following individuals, and we can see the variables. There are no classes on Thursday. We are on Thursday break. So we've sorted it right here. And what we want to predict is we want to predict the A class and the B class. Good to see you here, Nolan. So we've got the A class and the B class. And with the A class and the B class right here, our hope is that we could use something like either rating or gender to see how well it predicts. So we need to first do some stuff right here. We need to look at the Gini Index. Gini Index is going to show us how well this model predicts. So what is the Gini Index of this partition right here? Pretty easy to tell. So I want people to look at this partition right here and tell me the best possible Gini Index of it. What is the best possible Gini Index? What is the best possible for 1,000,000 points, first person answers for these millions we're going for? What is the best possible Gini Index? Things we should know like that. Careful. Gini Index is impurity. Gini Index is impurity. Gini Index, Ali got it right there, 1,000,000 points. Gini Index is impurity, so the higher the Gini Index, the more impure it is. So we don't want impurity. We don't want impurity. So a Gini Index of, a Gini Index of 1 is the best possible. My brain flipped for a second there. So what we do is we look at it this way. This is going to be the easiest way to see what's going on with this. And when we look at this, what percent of the time, I want someone to tell me as a fraction, do we have here the A class? What percent of the time do we have the A class? We have the A class, what, for 1,000,000 points? Easy questions right here. The A class we have what percent of the time? Do it as a fraction. You can do it as a decimal, technically. It's easier to understand as a fraction, I think. What percent? We have 3/8. John got it. And what percent of the time do we have the B class? 100,000 for almost answering. 1,000,000 first person. I'll call out your name. So what percent of the time do we have the B class? B class is 5/8. Caleb, nice job right there. So we go down here to compute the Gini Index. Always remember you can insert this right here. And so we can call this Gini right here. And let's store this into here. And the Gini Index is computed by doing 3/8 squared. And we also want to subtract from this. And I think it'll do it in the order. We'll make sure it does it correctly. Sometimes I like to, just depends on how you want to write it. What we're doing is, and I'll do a mathematical check on this because I know, does that look about right? That looks about right. Yeah, it looks about right. I know this should be 0.5 because that's 1/2 squared, 1/2 squared. So yeah, that's 0.5. And then if we were to do something like this should be 1, not that. So this should be 1 right here. And then the Gini Index is 0 because that is, let me make sure. Yeah, Gini Index is a measure of impurity. Hopefully I said that right earlier. My brain sometimes flips on this too. Gini Index is a measure of impurity. So the best possible Gini Index. Did I make a mistake? Oh my gosh. Aaron, you get 5,000,000 points. Because why would you want impurity? I've been saying it the whole time. Gini Index is a measure of impurity. So why would you want impurity? You want impurity to be 0. It should be 0. Sorry there. Oops. That happens every once in a while. Our brains just flip things back and forth. But then we check it and we say, wait, that doesn't make sense. Gini Index is a measure of impurity. Why would you want a high level of impurity? You want a low level of impurity. So the best Gini Index, please scratch out your note right there. I'm very sorry. Hot lights. There's very bright lights on me right now. And so makes way more sense. Yeah. So if you watch what I was doing right there, you would want Gini to be 0. Gini closer to 0 is better. Sorry, Aaron. Gini Index closer to 0 is better. You got to remember Gini Index is a measure of impurity, and then you have to say, wait a minute, do I want high impurity or low impurity? You want low impurity. So Gini Index closer to 0 is better. And we just showed it mathematically here because think about this. If everything is all the A class in this leaf, there would be 8 out of 8 A class, and it doesn't matter if it's A or B in that instance, and then there'd be 0 out of 8 of the other class, and we'd get an impurity of, if you can't see it above my head, 0. Well, watch this. I can reach up and actually touch that up there. If you can't see that Gini Index impurity right there, it's 0. So I've actually got a lot more room to reach out. So much room for activities in this room now with a big green screen. So really awesome stuff going on right here. So this is the Gini Index of this right here, and we're going to compare it now in a moment. So we're going to use a rule of 3.6 to split this tree up. And now let's see here. We're going to go to this one right here and split it there. Now we have to be very careful because we're going to have to do a weighted split on this. This is what's important right here. To figure out how well this does, you can look at this right here and say, how well classified is this? How well classified is that one right there? How well classified is that? Anyone have any idea? Million points. Who knows how well classified that is? Any ideas? 2/3 is right. It is 2/3. Whoops, wrong thing right there. It is 2/3. So we have 2/3 right there, and then this one right here is what? This one right here is what? Ah! It is... What is that one going to be? There we go. That one is going to be... I make one mistake, then I get a little bit afraid. I'm like, no! Can't make any more mistakes. Perfect. Yep. That one is going to be 4/5. So people in the chat should be saying 4/5 right now. 4/5. So, oops, yeah. 4/5 correctly classified, but it's still 1/5 incorrectly classified. So we've got our 2/3 and 4/5. So let's go down right here and let's put this in. And let's go here of Genie. Let's call it Genie 1. This is like Genie of trying just one split right here. And what we want to do first is probably go in and write, we could write it out this way. Genie 1 equals 1 minus, and then we need to do 2/3 squared. Wait a minute. Genie of set 1 is 1 minus, and this is where the mistakes are often made, 2/3 right here, and then 1/3. So we're getting the Genie. Let me point this out. This right here, this what I'm showing you right now, is the Genie of this right here. I'm getting the Genie of this, and then I'm going to get the Genie of this. This is the first leaf at the bottom. This is the second leaf. So let's go ahead and take those. We got Genie 1, and then we're going to go here and do Genie 2. And so let's make sure that's labeled Genie 2. And like I said, that's where the mistakes are usually made. And so we can look at the Genies over here. They're above my head right there. There's the Gini Coefficients. And if you think about it, the second one has a lower impurity because 1/5 and 4/5 is more pure than 2/3 and 1/3. So luckily we accurately see that the second one has a lower impurity. Now what we have to do is we need to calculate, let's call it new Genie right here. So we'll go new Genie. So, and then we store it in right here. And what we're going to do is we're going to take a weighted average of this. So we need to take 3 times Genie 1, or excuse me, 1/3 of this one. Probably easier to do that. 1/3 of this one. My brain is just breaking down today. 3/8 of this one times Genie 1, and I'll explain why we're doing this. And then 5/8 of this one times Genie 2. And there we go. That should be it right there. I'm going to double check the answer because my brain's just like, too much. Yep, it's the right answer, of course, because it's a weighted average. So when you think about this right here, all we're doing, and I want us to look at this mathematically, because it helps if you try to think about why are we doing this. Because the split right here only has how many observations in it? The split right here only has how many observations in it? 3 out of the total of the 8. The split right here has 5 out of the 8, so we're doing a weighted average on this. Does that make sense? David, million points right there. We're doing a weighted average on this to say, okay, well, let's take it weighted to what we have going on right here. And now we check another one. So we're going to do it on gender, male, female. And we're just doing the same process. So we've got most of the code written, just nice and easy right there. And can someone tell me just what I would write formulaically? Does everyone see this right here? Pretty easy to see what's going on. 2 and 3. Does everyone see what I'm saying? 2 and 3. So you can probably tell that this one's worse because this is a 50-50, which is not good. And then this is a 3/4, 1/4, which is, I mean, the 1/5 was way better. So all we're going to do is take this same thing we've just written and we go right here. We input a new thing right here and we just change the numbers. So we just change this to that, and this, and we go here, so that's 3, and that's 4, and then we go 4 and 4. Does this make sense right here? And we should get the new Gini coefficient for it, and the new Gini coefficient is 0.53125. Please notice what I'm changing right here is this represents, right here what I'm showing you, represents the following right here. That's what it represents. There are 2 out of 4 and 2 out of 4, and that's why I put this right here. Oh my gosh, someone call me out. There we go. That is the new Gini right there. So this right here is not really going to be as good as the last one. We can hide our last code. Sorry. Oh, wait. I need to slow down, everybody. What did I do? I got too much code. Did I just like erase my code? This right here is correct for this one. I think I overwrote my code, or I just wrote over the original code because I wanted to go down here. Sorry about that. I need to slow down. Wouldn't G2 on that be 3/4, 1/4? Yes. Do I have that written right now, don't I, David? So I have it written right there, and this one is 2/4, 2/4, 1/4, 3/4, and then the weighting on it is 4 out of 8, 4 out of 8. Are there any question on any of these numbers, on why I'm using anything right here numerically to figure out? I think it's backwards, right? Oh, shouldn't matter. It'll give you the same number, just so you see. It should right here, because this is like 4 minus 2 minus 1. So when you do that, you would get like 1 either way. So we can show right here the new Gini. We'll just type right here new Gini. And so we get that. And then let's reverse it. And so we should, when we highlight this, get the same exact number. And we do. So where each number comes from again? Sure. So this right here represents the first split. And all we're doing is using the Genie calculation on this. This is how Genie is calculated. You look at the number in each group that is the majority level, and you square it. And then you look in the non-majority and square it. So we have right here that the majority level for this leaf is 2 out of 4. And the non-majority is 2 out of 4. Does that make sense there, Christian? That we have 2 out of 4A and 2 out of 4B. That's what this represents, 2 out of 4A, 2 out of 4B. And then this one represents 3 out of 4A and 3 out of 4B. But this is the Gini of the second one right here. And I think I said 3 out of 4B technically, and then 1 out of 4A. So that 1/4 right there is from this right here, that A occurs 1/4 of the time. Then we do a weighted average. Why is it 4 out of 8 this time? Well, because in this one, we have in this this partition right here, there's 4 observations. And in this partition, there's 4 observations. So last time it was 3 and 5 because there were 3 in the top partition and 5 in the lower partition. So, and you see why this is 2/3 and this is 1/3. And then this is 4 out of 5 and this is 1 out of 5. And then when we multiplied for the last part, we did 3 out of 5 for the first one because there were 3 out of 5. And then 5 out of 8. 3 out of 8. Oh my gosh. 3 out of 8 and then 5 out of 8. Does that make more sense, Christian? There's a lot of numbers to know where they're coming from, but doing these calculations right here, pretty key, knowing how to do them. All that good stuff? I think we might be good on that. So when we look at this right here, we can look at the reduction it's using. So got it, awesome. So when we look at this partition, we can look at its before and after. What we want to do is we want to compare the reduction of it. Now, what we would love if it had a reduction close to 1. So let's write out some very quick stuff right here, and I think we have time for the sums of squared error. And you split it based on what it's sorted by. Yeah, well, when you do this in actual, like, using the models, you would tell it to split on male-female, so it would do this naturally. Like, you would tell the model split on, well, the model would search, and it would find, like, it's going to split on male-female, but male-female does worse than splitting on a numeric value right here. So actually, it might even do better, truthfully, if we split it right there probably. This is probably, that might be better. We'd have to calculate the Gini coefficient, which truthfully would be very easy to calculate. The Gini coefficient for this one, who knows? Try writing this out. Pause the video and try writing the Gini coefficient for this one if you were to split it this way, which we didn't ask, but it's always good to know how to do these things. We've got our code written out, so all we have to do right here is go up to this and take a look at it. So you see how there's 3/4, 1/4. So this one would be 3/4, 1/4. And then there's also this. So the Gini coefficient here would be the following. The new Gini coefficient would be 0.375. So that is the new Gini coefficient. Now, if you notice, I did store the original Gini coefficient right here. This is going to be key. I'm going to do the last problem right here, seeing about how it would actually work. So what we're going to do is we are going to take our original, let me write this out as a different way. We are going to take our original and subtract from it our new, and then divide by the original. So what's the whole point of this? Is to kind of standardize the difference. And what would we like our new Gini coefficient to be? What would we like our new Gini coefficient to be? Now this goes back to my first question I got wrong, but what would you really like that new Gini coefficient to be? Any ideas? What would you like that new Gini coefficient to be? 0, you're right. And then what would this solve out to? If the new Gini coefficient was 0, what would the reduction be? The reduction would be what? A million points, all those answers. The reduction would be this. And just look at how the formula works. You would want a reduction of this, and it makes sense. You'd want a reduction of 1. Yes, exactly. A million points are there, Aaron and Kyle. So you'd like this right here. So we've got our original Gini right here, and then I called the other one new Gini. Does it? Yep. So this is our new Gini coefficient right here. And then we've got the original Gini. And we should get, yep, that's what, let me double check that one. Always afraid, always afraid. So the Gini rating right there. And I'm seeing a little bit different. There's the weighted. So the 4/8, let me double check. So we should be getting this right here. Oh, there's the reduction. We haven't seen the reduction yet. I'm going to make sure. Well, let me make sure. Oh yeah, it's better. The rating is better because it gives a, oh, it doesn't even ask. Oh, it's not in there. So which one of these is better? It's actually asking. I did something we didn't have to do. I do that all the time apparently. So when you look at this right here, which one is better? The one that is going to be better is going to simply have the new lower Gini coefficient. And right now, the reduction's not that great. If we used a CP, if CP was equal to 0.10, would we make this split right here? This is where I wanted to go with this question. If CP was equal to 0.10, would this split happen? Like if this is our best split, would the split happen if the CP is 0.10? And this goes back to understanding what CP is and what it does. Would the CP happen? Would the split happen with this CP? The answer is no, Aaron, million points right there. It would not happen because this right here is not a large enough reduction. Julio right there, million points, and Jessica. We would not get this split if this was one of the splits we could do because it does not meet the reduction we need. So the CP is the reduction we need. Once again, if we put the CP to something like 1, what will we generally get for our model? Very high CP, all of a sudden now your trees are very, very what? Well, obviously this would give you the what? Your tree would be very, unless it did a perfect split, you'd probably get something close to naive. I think we have time for just doing the sums of squared error one. I will come back and do the rest of this. Which of the tool rules will be chosen? This or this. This one was better. And why? This one would be chosen right here because, and it would be underfit, because it would be the naive. It would be very underfit, because the tree would not be able to split if we put a high CP. So it would be very underfit, very small tree. So this rule would be chosen because it has a lower new Gini coefficient when we make the split. It does a better job at reducing it. So we could calculate both reductions if we want. All we have to do is just take the old one, the new one, and whichever one has the better reduction, whenever you calculate this, that would be it. And just to show you real briefly here, I think we've got the numbers memorized. This one is this right here. It's 2/3, 1/3, and then this was 4 out of 5, and this was 1 out of 5, and this was 5 out of 8, and then this was 3 out of 8. So we're going to recalculate our Gini coefficient there, new Gini coefficient, and then we can look at the reduction, which was 0.0667, and then we go right here, and that's the reduction. So which one did better? The one where we split on the quantitative value had a better reduction, and thus it would choose to split on that. So that was a lot on Gini coefficients right there. So last but not least, we're going to do these sums of squared error. Oh, we'll go till people have to leave. It's all right. I'll put it in here till 2. So a prediction model currently has this right here, but now we're doing a quantitative value, this y value right here. What day will you do? I could do it like on maybe Thursday, even though we don't have class. Would that work for people if I do it on Thursday, like appear online? Maybe I'll do it and it'll be recorded so you can watch it at any point. So it'll be on here and I'll basically give away the answers. Is everyone cool with that? If I do it on, should we end class now maybe, and I'll come back and I'll do the sums of squared error one? I always hate going through stuff too quickly. There's so much material in this course. And does that work for everybody to have the lab to work with? that we do it as a video, and you can watch the video, and it basically good. Always, Saeed says. Thank you, Saeed. Million points. David likes that too. So I want you guys to have access to it and knowing how to do it, practicing these models, because tree-based is coming up for the homework. I'd rather take our time. So I wanted to do 2 of these right now, but I want to take all your guys' questions. Let's do it during regular class time on Thursday. You don't have to be here. It's not required. It is recorded, and I will work through all problems. I will take all questions. I will go as slowly as possible. And so probably I won't be doing like Stat 201 that day. So we could do it over a longer period of time. Remember, you can always fast forward, rewind these videos. You can put notes in the video. So if you want to put like, hey, Brian works at this problem at this time, probably don't put it in the comments like, hey, the answer to this is this. But Saeed's checking his points. But we're able to work through one of these right now and see how the Genies are calculated. Be very careful. It's easy to make mistakes, but do understand the theory stuff like this right here. Like, how are we comparing them to look at the reduction? Know the formulas. You can write them down. We'll allow you to write things down in this class. It never hurts. That what we have right here is the first split right here and the second split, and then we have a weighted average of the new Gini coefficient. And then the big thing we do is we compare how are they doing. Everyone's checking their points now. But great job today, everybody. The new lights are so much brighter on me right now, so I'm getting used to the bright heat lamps on me. Like if you look, it's literally like the sun on me right there. Like that's where I put my hand towards it. And then, but I do have so much more room on the green screen right here, so it's a lot of fun. And I thank you guys so much, Caleb and Ali. Wow, leading the way right there. So keep growing the beard. I'm gonna try. It's getting somewhere now. We'll try. Only one other time in my life I've actually attempted to grow a beard, and I failed. So we'll see what happens with quarantine beard. So we'll see what happens. Thank you for the encouragement, Saeed. Million points right there, Saeed. So we will head off here in a second. But any other last few questions as we are finishing up class? I'm thinking about 201 now. I'm like, okay, I'll be teaching them in 15 minutes. But we got everyone checking their points. And I will be looking at Streamlab points at the end of the semester. So the more you're on here, the more you're interacting. I will also weight that into your points. So keep coming to class, keep talking during class. The more, it's like where's the office hours link again? You'll see it on the channel. I'll actually be live on YouTube. If you ever see me live on YouTube, it's just the YouTube thing. So whenever you see office hours, you should see me streaming on YouTube. And I might go over to Twitch, but that might just cause confusion. We're trying to plan out an interview with Julio. We did some testing yesterday, and that's why I was also doing like, but we've got it pretty much set up. That's why I have the speed run over here. I might actually do it via this screen. So we haven't gotten our points back yet. Anyone can subscribe if they want. You don't have to. But all this good stuff right here. And so hopefully we get the interview. Same hours as usual for the office hours. Yep. Did I send out the announcement with it? I'll be here right after Stat 201 today from 5 to 7 doing the office hours. And so all that good stuff. You're welcome, Spencer. Thank you guys so much. I'm glad. I hope you have fun during class. I hope it's like, I want people to enjoy coming to class, even though we're all online now. And so I can do my speed run timer. So I've done 18 speed runs. I win them all. So I think we'll head off here a moment. I'll start preparing for 201, but email me those questions if you got it. I might have missed the albums, but just making sure. Yep. And I might send it out again. Sorry, I might have so many things going on. And thank you we got a lot of people stepping up to help 201 out because you guys are still a huge priority for me too. But God, we're making sure everything's working well. Will you work the lab problems in a separate video? Yep, Ali, we will do that on Thursday during regular class. We do not have class on Thursday. Anyone watching this video, we do not have class on Thursday. But Brian will work through all problems on Thursday so you can have a full video you can watch on your own time. You can join on Thursday. If no one's here, I'll just work it by myself. It won't be as fun, but you don't have to be here because we don't have class on Thursday. I want to see it in the chat. Million points for everyone who says we don't have class on Thursday. You put parentheses, but you can watch the video live if you want. You don't have to. There's no penalty. There's no nothing. I'm just gonna make an extra video on Thursday where I'm live doing stat lab or doing the lab. So first, who gets the million points? We don't have class on Thursday. So I'd hate for someone to be like, Brian, did you hold class? I'd be like, no, I'm just helping. We do. Saeed, you well earned that million points. We do not. Or else there's some good prize. Awesome. Cool. Well, I'll let you guys and gals go. We do not have cluster, but you can watch Caleb million points right there. Okay, I'll see everybody later and maybe see you on Thursday, but we don't have class on Thursday. I'm just doing a lab to help you guys out, and you can watch it on your own time, and that's just to help you guys out. Talk to you guys later. Have a great day.